Okay, we are closing in on the end of the never-ending chapter 14. So we're going to go over this example, which of course you worked out. You can follow along with the workout part on yours as we go through it, or just fill it in, I suppose, as I do it, whichever one is the correct answer there. I'm afraid I know the correct answer. All right. So this is a titration problem. It's going to take us through some different points in a titration. We did talk about pretty much three different types of titrations. We talked about titration of a strong acid with a strong base, a titration of a weak acid with a strong base, and we talked about a titration of a like strong acid with a weak base. I think that was right. So, you do want to sort of identify what type of titration you're dealing with. And really on all the titration sort of curves, there's really four sort of distinct points that are of interest. Usually it's before you start the titration, kind of like your initial pH of the solution. Then we have pretty much from the start of the titration up to the equivalence point is usually the next sort of section of the titration. Obviously, in that case, you will get some reaction that's going to occur. And as we talked about a number of times, obviously with titration, you're doing nothing but continuously changing the volume, which means, again, those initial ice tables should be done in moles. Because of that, you could convert back to molarity after the first ice table, but definitely got to do that first one in moles. Then we reach the equivalence point, which, again, depending on the type of titration you're doing, you have some different things that may be happening at that point. And then the fourth part is going past the equivalence point and basically just continuing on with your titration here. So let's take a look at this particular one here. We got 100 milliliters of 0.1 molar nitrous acid, and we're going to titrate it with some sodium hydroxide. Nitrous acid is a weak base, a weak acid. That'd be better. And sodium hydroxide obviously is a strong base. So this is a titration of a weak acid with a strong base type titration. Again, I know it is a weak acid because I do see a Ka value given to me as well. So that's a pretty big hint. So again, we're going to take a look at this, and for orientation purposes, in this titration, we are adding the sodium hydroxide to our acid. So again, adding the sodium hydroxide to our acid in this case. So we'll start with A here, which is the initial solution. So that's before we've added any sodium hydroxide. So that is really just our weak acid that is sitting there. So as we talked about in this type of titration at the very beginning, it is just a weak acid problem like you just did on the quiz, hopefully. So let's see. So because this is our initial one here, we're basically going to get our weak acid that's going to dissociate into H plus and NO2 minus. And we had a Ka value there of 4.5 to the minus 4. So Ka value of 4.5 times 10 to the minus 4. So remember here, we haven't added any sodium hydroxide, so we could just do this in molarity, just a regular sort of Ka table. That means initially here we had 0.1 molar. These guys would be 0. Our change here would be minus X plus X plus X. And that would give us at equilibrium 0.1 minus X, X, and X. Any questions on the table here? This is going to go into our Ka expression, which in this case is going to be our products over our reactants. Once again here, I don't have it in my equation, but if you had water in there, you obviously would leave it out as well. That's going to equal 4.5 times 10 to the minus 4. Putting in our values gives us x squared over 0.1 minus x. We could assume that x is equal to 0. And if you did that, which I'm sure you did, and I'm sure when you checked it, you got something like 6.7%, which made you feel really sad doing this problem last week when I assigned it, and know that the check is not good. So if you did the assumption here, you're going to end up with a X value, I think, when you check it, or a percentage there of 6 and some change, which is too big. So to save some room here, I'm going to then do obviously the quadratic formula here. That means I'm going to multiply this guy to the other side. And when we multiply the guy to the other side there, that's going to give us x squared is equal to 4.5 times 10 to the minus 5 minus 4.5 times 10 to the minus 4x. Combining everybody to the same side, gonna give me x squared plus 4.5 times 10 to the minus 4x. And I believe that then becomes a minus 4.5 times 10 to the minus 5 is equal to 0. That's going to give me obviously my A, B, and C action here, right? A, B, and C. So going into our quadratic here, we get x is equal to minus b, which is minus 4.5 times 10 to the minus 4, plus or minus. When you put all the numbers into the square root, I believe you end up with 0.000180, for which you take a square root of that and end up with 0.0134. That will all be divided by 2a, which in this case is basically 2 times 1, which gives us 2 in this case. This is again going to give us 2 x values here. So I'm going to do the plus first. So minus 4.5 to the minus 4 plus 0.0134 divided by 2 gives us an x value of 0.006475. We do the subtract there. Gets us a x value of minus 0.006925. Once again here, since we are interested in the pH, which is equal to x, we clearly cannot have a negative number here. That means we should probably roll with the positive number. That means in this case that x would equal the H plus concentration, which would be 0.006475. That then could go into our pH. And pH of about 2.19 here to open up. Yeah. Any questions on any of those steps there? So this is just a regular sort of Ka problem because we are basically just starting with a weak acid at this point. Any questions on that there? Okay. Then let us take a look at the next part, which is B. In this case, we're going to add 80 milliliters of our sodium hydroxide here. So obviously the titration has begun. So here for B, we have 100 milliliters, I believe, of 0.1 molar HNO2. Here we're going to add 80 milliliters of 0.1 molar sodium hydroxide at this point, right? All right. All right, so obviously the reaction has taken place. So we will write our reaction here, which will be HNO2 reacting with some sodium hydroxide here. Going to give us a little sodium nitrite and a little H2O action happening here. In this case here, we need to do an ice table, and it should be done in molarity or moles. Should be done in moles, so we do need to convert these guys into moles. So that would be 0.1 liters times 0.1 moles per liter. And that would get us 0.1 times 0.1. 0.01 moles for our nitrous acid, and same thing here, 0.08 liters, which is our 80 milliliters converted to liters, 0.1 moles per liter. 0.08 times 0.1 gives us 0.008 moles of our sodium hydroxide. So putting our numbers into the table here, HNO2 0.01 moles and 0.008 moles for this guy. Once again, this is what I'm adding, right? This is what I'm starting with. That means, am I before, at, or after the equivalence point? I am before the equivalence point here. My sodium hydroxide moles are less than what I started with. Remember, at the equivalence point, they're equal. So if what I'm adding is less, I am before the equivalence point, right? If what I'm adding is more, I am past the equivalence point. So because they are less moles are being added, we are definitely before the equivalence point, which means we should already know pretty much the type of thing we should end up with. So let us see if we do. Because of that here, this guy is really the limiting reagent. So the change here would be the moles of our sodium hydroxide, since we do have enough moles of our acid to take care of it. That means here we will end up with 0.01 minus 0.008, 0.002 moles, 0 and 0.008 moles. Our total volume at this point is, we started with 100, we added 80, that's 180 milliliters. So at this point, we want to convert it back to molarity. We're going to take this guy here and divide it by 0.18 liters, 0.18 liters to convert these guys back to molarity, gives us 0.0111, we'll call it, and 0.0444 molar. Any questions on the ice table here? Once again, if you're not sure what's going on, you can use your ice table to help you out. We have basically this guy left over, and we have that guy left over. Are these two guys related to each other? They are. That is a weak acid and its conjugate base, which means this is a buffer, right? Which is exactly what we would expect to be happening in this type of titration before the equivalence point. So once again, understanding what you should expect can help you out with the calculation part. So because this is a buffer, we can do one of two things at this point. We could do another ice table, which I don't know if you really want to do that. Probably the safer move is to go right into our Henderson-Hasselbalch equation here. We do need to calculate the pKa value. So that would be our pKa is equal to minus the log of the Ka value, which would be minus the log in this case of 4.5 times 10 to the minus 4. So minus log 14, no, minus log 4.5 to the minus 4 gets us 335, looks like. So the pH here would equal our 3.35 plus the log of the base. This one here is the base, right? Because that is the sodium nitrite, and that is nitrous acid, which would not make it a base, obviously. So we want to go with 0.0444 up on top, 0.0111 on the bottom. A little log action of it. Then we're going to add it to 3.35. Gets us a pH at this point of about 3.95. Questions on that? This does make sense since we started with a pH of 2.19 and we're adding base. So we should see the pH start to rise, right? So it didn't rise by a lot because we're in the buffer region of the titration. So it's really buffering right now. So what's happening at this point in the titration is you have a buffer. You haven't blown through your buffer until you get closer to the equivalence point. And that's why we see a big jump in pH like we talked about, because right now you have a nice buffer that's made. And it's basically being able to be a buffer. But as you continue to add sodium hydroxide in this case, you will blow through the buffer part of it, and you'll see that big jump in pH to the equivalence point. And that is where we're going next, I think. Any questions on this here? All right. So as we talked about last week as well, this is, again, a way that you can make a buffer from one component of it. So for example, here we had the weak acid, we reacted it with a strong base, and we were able to make a buffer. A reminder that it is not the sodium hydroxide that is part of the buffer, it is actually this guy at the very end that's left over that actually is the buffer. So again, that's the way you could kind of make a buffer from a reaction of a weak acid and strong base, or a weak base and a strong acid. What is left over at the end result there is a buffer. So let's look at this one here, which is C, and we're at the equivalence point here. So same titration, continuing on to our equivalence point. So C is, we have again our 100 milliliters of our 0.1 molar nitrous acid. And we're adding our 0.1 molar sodium hydroxide, and we are at the equivalence point here. Equivalence point. So obviously in this case, we are going to have our reaction that's going to take place, which is our HNO2, our sodium hydroxide, still reacting the same way. Going to make our NaNO2 and our H2O, right? We obviously want to do this in moles. So once again here, we will get moles of this guy, which will be our 0.1 liters times our 0.1 moles per liter. That gets you our same number there, 0.01 moles. So that brings us to this question here, which is the moles of sodium hydroxide, right? We are at the equivalence point. So there's a couple of ways you could figure out the moles of sodium hydroxide, and maybe even more important, the volume to reach the equivalence point, which it did not tell you. One way is, I know the moles of my sodium hydroxide should be what number? Should be that number since it's at the equivalence point. So, well, frankly, I already know that this should be that, which means I have molarity, which is moles per liter. I know the molarity, I know the moles. I could find the liters by taking the moles divided by the molarity, would be one way that you could do it. And again, in this case, that would give you 0.01 moles divided by our 0.1 molar, which is moles per liter. And that would get you 0.01 divided by 0.1 gives you 0.1 liters or 100 milliliters to reach the equivalence point. The other thing you could do is M1 V1 equals M2 V2, because it's a 1-to-1 relationship, which means the stoichiometry is 1-to-1. So this will work. Once again, it will not work if it is not a 1-to-1 relationship. You actually have to do the stoichiometry calculation. So again, here you would take 100 milliliters times 0.1, which is the acid. And this would equal our M2, which is what we have there, 0.1 molar, and V2. Solve for V2, it will equal 100 milliliters. So there's two ways that you can do it. But one way, anyway, you need to know obviously the volume so you can convert everybody back to molarity. So you do need to know that. By the way, if the concentration of the acid and base are exactly the same, and it is a one-to-one relationship, you need the exact same volume to reach the equivalence point always. So in this case here, that is how we could get to the moles, one of those ways. Our change here at this point, you really can't pick the wrong number because there's only one number to pick. So we'll pick that number here. That means when we do reach equilibrium here, we got nothing here, nothing here. We do have 0.01 moles here. We once again are going to convert back to molarity by dividing by 0.2 liters in this case. And that is because we started with 100 milliliters of the acid. We figured out there from our calculation, we needed 100 milliliters of the base. Gives us our total volume of 200 milliliters converted into liters. 0.01 divided by 0.2, that is a 0.05 molar. At this point in the titration, we pretty much have just one thing left here. What is that thing? That thing is I'll circle green as well. Circle it this color as well. This is what? I'm running out of colors. I'll circle the red. That is a salt, right? And when we have a salt, we want to know, will it go through hydrolysis? And the answer is, will it go through hydrolysis? It will, because it comes from a weak acid. So in this case, we have the sodium nitrite, which will break apart into a sodium ion, right? And a nitrite ion. The sodium is neutral, and it is the nitrite here that will go through hydrolysis. And as was mentioned, since it comes from an acid, it will act as a base when it goes through that reaction. So we will have a second ice table here, which is this part of the salt reacting with the water. And once again, because it's going to act as a base, it will accept the H plus coming over. The result of that is we will get back our weak acid it came from, and we will produce hydroxide here, which means we will expect this pH to be acidic, basic, or neutral. Should be basic because we are producing hydroxide here. So once again here, we're going to use our equilibrium value from the first table for our initial value of the second table. So that's going to be 0.05. The rest of these are going to be zeros and x's here. Minus x plus x plus x. This is going to give us 0.05 minus x, x, and x. This will go into our K, which is our products, divided by our reactant. And by the way, this is a K, A, B, C, D, E. This should be a KB because of the hydroxide. So here we will need to convert the KB value, or to the KB value. So I'm just going to do that on the next page here, if that's okay. So our Ka value here was 4.5 times 10 to the minus 4. Ka times Kb equals Kw. That means that the Kb here would be 1 times 10 to the minus 14 divided by 4.5 times 10 to the minus 4. And that's going to get us lots of twos. 2.2 times 10 to the minus 11. So going back to our KB expression, that is going to give us x squared divided by 0. There's 0 in that, I don't remember there. 0.05. minus x will equal our 2.2 times 10 to the minus 11. Here we could assume x is equal to 0. That will give us x squared divided by 0.05 is equal to 2.2 times 10 to the minus 11. Once again, we're going to multiply to the other side and also take the square root of it. And when we do that and take the square root, we end up with an x value that is equal to, I'll call it 1.05 times 10 to a lot. 1, 2, 3, 4. Minus 6, if I counted that right. Yeah. So we do want to check it. So we're going to take this, we're going to divide it by 0.05, times it by 100. So take that divided by, whoa, that's definitely the wrong number. 1.05 minus 6 divided by 0.05 times 100, and the check here is good. So that means that this value here is going to equal, if we go back to our table, not the H plus, but the hydroxide concentration. So again, important to remember. So that X will equal the hydroxide concentration, 1.05 times 10 to the minus 6. That's going to give us a little POH action at this point. And that pH there will be 1.05 to the minus 6, a little 598. And again, if by some chance you were confused and you thought this was the pH value, it should not make sense because it should be basic. So we do want to take our pH would be 14 minus 5.98. Minus 14 looks like an 802, which is basic, and a much better answer, I suppose, at this point. So this is, as we talked about, at the equivalence point, you will always have a salt in this type of titration. That salt, because it always is coming from a weak acid, will go through hydrolysis and will always produce hydroxide, and it should always be basic at this point in titration. Any questions on that there? All right, one last spot here we're talking about, which is the letter D. We are at 105 milliliters of base added. So let's take a look at that. So D is, again, we're still starting with our 100 milliliters of 0.1 molar HNO2. At this point, we're adding 105 milliliters of our 0.1 molar sodium hydroxide. Once again here, we'll do our reaction. And once again here, we will start with our moles. So our moles of nitrous acid has not changed. And by the way, that's an important note as well. When you typically do titration problems and there's multiple parts, each part is sort of thought of as being separate, like you're starting at the very beginning and you added that amount for part A, and then you started at the beginning, you added to part B. So it's usually not in a problem, sort of a continuation where you keep adding up the volumes of stuff that you put in there sort of along the way. Here we would do 0.105 to convert it to liters times 0.1 gives us 0.0105 moles and 0. Now, clearly here again, since we just did the equivalence point, we should know that we are now past the equivalence point because what we are adding is more than what we started with. So we're definitely past the equivalence point at this point. This is the point of the titration where, because we are sort of past the equivalence point, we're really, in this case, just dumping base in there, which means our base is our excess amount and our acid is our limiting reagent. So this is where the change is now going to be the acid because it is the limiting reagent. So this would be minus 0.1. And again, logic tells us we cannot have a negative, guys. So you got to take the smaller number, 0.01. That is going to get us at equilibrium 0.000 moles and 0.01 moles. At this point, in terms of our total volume, we started with 100 milliliters. We added 105. That is 205 milliliters of total volume, which we could use to convert back into molarity here. And that would get us 0.205, 0.00244. And for our other guy, 0.0488. At this point, again, if we take a look, we got this guy left over and we have this guy left over. Are those two things a buffer? They are not a buffer, so they are not related to each other. So what we have left over at this point is a salt, and we have a strong base. So just like we saw in the previous step and talked about before, this guy here will go through hydrolysis. It will act as a base, but between NO2 minus and sodium hydroxide, which one is the stronger base? It is the sodium hydroxide. It's going to be really the major contributor here. So it is at this point in the titration where, although this guy is contributing a little bit, pretty much this is going to be your major one that's going to contribute, because all it has to do is go into the solution to produce hydroxide in this case. So because of that, that is our hydroxide concentration, because that is a strong base. And that means, once again, at this point, we can get our POH, which will be this guy here. $261 looks like. And once again, getting to our pH by taking 14 minus that gets us an 1139, which is definitely basic and is what we would expect to sort of happen here, as we are really just dumping basically pH in there. Any questions on that there? So this obviously a weak acid, strong base titration. If you just think about, pH wise, sort of where we started and where we ended, we had right there like a 2, right? And then we had a little buffering action of like a 3. Then we jumped to like 8, and then we jumped to like an 11, right? Which gives us that kind of S curve type of shape that we have. And again, as we're coming through here, we're buffering, we break the buffer basically, and we get that big jump in pH as we approach the equivalence point and really past the equivalence point as well. Any questions on any of those types of calculations? You should now be professionals that can calculate the pH anywhere I should ask, or if I'm really mad at you, like all 300 points of a titration curve. It's going to be a fun test. So calculate the first 400 points of this titration. They did it drop by drop by drop. All right, to finish up this chapter 14 here, we talked a little bit about acid-base indicators. We talked a little bit about them before, but again, acid-base indicators basically will work over a selected pH range. And really, depending on sort of the concentration of kind of the protonated form of the indicator to the deprotonated form, as to what color you will see. Indicators are really like weak acid, and that's basically the indicator that has the H plus still on it, like a weak acid. And this is sort of the deprotonated indicator, just like the weak acid would give away its H plus, and it comes off. So if that ratio, basically the protonated or the acid form of the indicator over the base form of the indicator is greater than or equal to 10, we'll see the acid sort of color. If it's sort of the opposite, if it's less than 10, then we'll kind of see the base color sort of occur. Now, depending on, the pH range that you have for that indicator, you typically will see some type of color change as the pH sort of increases. The goal of selecting an indicator is, in most titrations, we usually want to stop at the equivalence point. So we usually want to select an indicator that will actually change color when we get near the equivalence point. For example, phenolphthalein, like we like to use a lot, which is down here. As you can see, it is pretty colorless there in the early 8s to close to 9. Gets to that really kind of light shade of pink, and then really that kind of darker pink as we get past to like 10. That again is why they would yell at you that you want the lightest color pink, because that should put you back over here, which is roughly probably where the equivalence point is going to change, 8 and some change. Would something like, say, creosol red be a good indicator to use in a titration that you would have used, say, phenolphthalein for? Would it work as well? It would not work, because creosol red, after it hits wherever that is, like 2 and change, that's going to be orange, right? Which means it's going to be orange a long time as you do your titration, which means you're not going to get a visual change, right, in the color to tell you to stop, right? Because it has already changed this color way back there around a pH of 1.5, right? So you want to definitely choose one depending on the type of titration you're doing, where you expect the equivalence point to be. You could actually do a theoretical calculation to figure out what your equivalence point pH should be. And you could have a choice of indicators, really narrow in and dial in on one that would be really, really good for you to use. So for example, if we did this titration like the one we just did, basically the calculations for which ones on this list here would be a good choice of indicators. So there's a bunch of indicators here, and their color in acidic solution and basic solution, and the pH ranges which they work. So take a minute here and figure out which ones would be good on this list. So let's take a look. So first off, HNO2, as we just saw, is what type of acid? It is a weak acid. KOH is what type of base? Strong base. So this is a weak acid, right? Strong base titration, which means when I reach my equivalence point should be neutral, acidic, or basic. Should be basic, like we calculated in the previous example, like 8.02 basic in that case. That means that if I went through the thiamol blue here, worked over 1.2 to 2.8, that's going to already change color way before that. So that's not going to be useful. Nor will really this one for the same reason. Nor will that one. Nor will that one. Not that one either. This one does get into slightly basic, but probably there's a good chance that the change has already occurred a little bit earlier than that. So that probably wouldn't be good either. This is in the basic range, which we could get a nice change that occurs. So that's a good choice, perhaps. And also phenolphthalein would be a good choice. So these two here would be good choices. And again, if you wanted to maybe narrow down between the two, you could do a theoretical calculation, and maybe one might be even better than the other to actually help you see the color change. Any questions on how to pick an appropriate indicator? Yeah. If I was doing say a opposite one there with a weak base and strong acid, which ones would then be good? Weak base, strong acid, we expect the equivalence point to be acidic because it's going through hydrolysis and going to produce H+. So any of those sort of acidic ones might be a good pick. And again, you could do a calculation and really narrow it down based on what you are titrating with as well. Any questions on indicators there? All right. So that should wrap up, I believe, chapter 14. Yes.